Hey, this is Dr. B, and let's talk about titration. Let's say you have a acid that you don't know the concentration of. Well, if we can react it with base, at some point it will neutralize. The more base we need to add, the stronger that acid must have been. So that's typically how things are done. You start with a burette, which is a thin column, oftentimes 50 mils and graduated. Into that you place your base of a known concentration, and then you drip it into the acid. You measure how much acid you used in terms of its volume. And then you oftentimes solve these by C1V1 equals C2V2. In other words, you know the concentration of the base, you know the volume that got dripped in, you know the volume of the acid, but you don't know its concentration. Since you have 3 of the 4, you can solve that mathematically and you're good to go. Let me talk for a minute about the method before we solve a problem. Uh, there are things known as indicators that will change their color when they become basic typically. And phenolphthalein is a great example. So when you drip in the base, as long as you have like a drop of indicator present, once that thing switches over from acidic to basic, the moment it does, it will start to turn pink. And if you can hit what they call a pale pink endpoint, you have done it very precisely. You've got your amounts and you can run your calculation. I'm going to ask a question that's a little bit different, and let's go ahead and solve it. In a titration experiment, a student finds that 23.48 mils of sodium hydroxide solution were needed to neutralize 0.5468 grams of this substance, KHP, potassium hydrogen phosphate, K2HPO4. What's the concentration of the sodium hydroxide solution? Now, it's not very often that you do a titration in order to find out the concentration of sodium hydroxide, but this should do it. So we want it in moles per liter of the sodium hydroxide. So let's first convince ourselves that the stoichiometry is 1 to 1 and take a look at this. And that is 1 to 1. Everything is nice and normal. So we need to know the moles per of sodium hydroxide for liters of solution. And we have the liters of solution. It's 23.48 mLs, 1,000 mils is a liter, shifted over 3 decimal places, and you have 0.02348 liters of sodium hydroxide. If we can get the moles of sodium hydroxide, we're done. And since it reacted in a 1-to-1 ratio, the moles of sodium hydroxide is equal to the moles of the KHP. So if we can just get the moles of the KHP, that shouldn't be too hard. We should be done. And we only have 0.5468 grams of KHP, but a whopping 204.2 grams is a mole. So we have 0.5468 divided by 204 moles. That's not many at all. That is the moles of KHP. That's also the moles of sodium hydroxide. That goes on top. It's the 0.0234 liters on the bottom. Bada bing, you've solved the problem. So let's show it in all its gory detail here. There it is, set it up. We want the moles per liter. We have the liters. We just need the moles. And there's the moles of KHP. Like we said, very low number. It's also the moles of the sodium hydroxide. Now you have your top, you have your bottom. Run your calculation and you find that you have a 0.1141 molar sodium hydroxide solution. This is an introduction to titration.